take a look at a few more examples related to kind of practicing work and energy. So here's a few examples for you. You can go to any timestamp that you like if you want to skip over and go to a particular question. Okay, so you can look in the descriptions, okay, below to see what the questions are. All right, so an MRI machine weighs about 17,000 pounds. What is the amount of work done by a crane that lifts the machine to a height of 25 meters above the ground, and assume 1 Newton is equal to 0.225 pounds? All right, so let's take a look here. Okay, so we have given the following information. So we know the weight. So this is going to be the force of gravity that we're going to have to overcome. This is 17,000 pounds. However, we want this in newtons to make it in standard SI units. So I'm going to just convert it right away so that I have that out of the way. So here it is. So 17,000 divided by 0.225. So that's quite a few. I'm not going to round this. So 7. Okay, so that's a lot of fives there. So let's write it in 555 point. All right, and that's newtons. So that's the first thing. What is the amount of work done by a crane? So we have basically a height. Okay, so the displacement that we're going to have, which is the height above the ground, which is 25 meters. So we're going to have to be lifting this up. So we're going to have to overcome this gravity. This isn't actually very difficult. So the work is always the force that we need to apply, and then times the displacement, and then times the cos of the angle, although now it's all just upwards, so the angle is 0. So that means cos of 0 is equal to 1. So this is really just force multiplied by the actual displacement that we have. So that will be just these two items, okay, that we're going to have to worry about to try to figure out what the answer is. So I have already this on the calculator, and I have to take this and I'll just multiply it by 25, and we're going to get 1. It's quite a lot, okay, of work. There's a bunch of 8s there, as you can see there. Now I'm going to round this off. So if we're going to be rounding, I guess, to 3 significant figures, so it's going to be 1, 8, and 9, okay, and then 0, 0, 0, 0, okay. So we have, okay, so this is, I just want to make sure that I have 3, 3. That's correct. All right, so that's how many joules we would have, okay, of work that was actually needed, okay, in order to lift this thing up. That is it, okay, for this example. Here's a nice challenge example with regards to work. So this one isn't as common. So let's take a look and try to break it down and solve it. Okay, so what do we have given? So 225 kilogram object is sliding at a speed of 3.5 meters per second, okay, to the right. All right, so we have, this is going to be the mass, okay, of the object, 225 kilograms. We have the speed. Now this is, I guess, to the right, so it's actually a velocity. So this is 3.5 meters per second. This is to the right. We have a constant force of 95 newtons left is applied until the object stops. Okay, so let's draw this out. So let's say we have, all right, so here it is. We have 95. This is to the left. Now the object while stopping is under constant kinetic friction force. All right, so there's another friction force. This one's much bigger. So that's going to be in the opposite direction. Now this thing is trying to move in this direction, so we're going to get a negative work because you can see there that the displacement, if you're moving to the right, is going to be 180 degrees with respect to the forces that are applied. All right, so that's what we will have there. So compute the amount of work assuming the forces are present until the object stops moving. All right, so let's take a look here. So what do we need? Well, we definitely need, okay, the forces. So the net force is going to be 95 plus 397. Now this is to the left. All right, so Okay, so we have F net. Now, so the next thing is, so we want this, right? So this is what we're after. We want to know how far this thing has moved. Now, if you think back of kinematics and then your equations, so we typically will need, so we either need, you know, we don't have the total time here. We don't have the acceleration either, although we can find the acceleration in here. So in this case, it's going to be the deceleration. So let's start with that. So we're going to try to find the acceleration. So F net is equal to the mass times acceleration. So we know that we have that. Now, in the direction of motion, so this is actually going to be the opposite direction. So 95 plus 397. I'm going to put negative because it's to the left, all right? And we're sliding over to the right. The mass is 225 kilograms. So now we can find out what the acceleration is. So acceleration equals this divided by 225, because if you divide on both sides, now it's going to be negative because you're decelerating. So I'm going to just put that in. This is all in metric standard units, so that's in meters per second squared. You can keep that in mind for yourself. So we have now acceleration. Well, that's still not enough because we do need to kind of find out, okay, what what this displacement is. So let me just kind of go back and now start thinking about, okay, how am I going to get it? I guess I can certainly find out what the total time is, right? So I have that. Now I'm going to think back, okay, to kinematics, and actually, okay, I just recall that, okay, so we have V final squared is equal to V initial squared, right? Plus, this is going to be 2 times A times the delta D. So actually, I don't need the total time in here. Now, I have my V final, so that's 0 because we're going to stop. My initial is 3.5 squared. This is plus 2, and this is going to be negative 2.186, etc., times delta D. All right, so this is what we're going to have over there. So let's take a look. So now I'm going to bring this over to the other side. So that's going to be, so 3.5 squared. It's going to get over on the other side. So that's going to be negative 12.25 equals to negative. This is going to be, notice now, 2 times the 2.186 delta D. So my delta D, okay, is going to be negative 12.25 divided by, and this is negative 2 times 2.186, etc. Okay, so I actually can obtain my displacement in here. So the negatives will cancel. So that's what we're going to have. So we're going to have our answer in here divided by, this is 2 times, and 2.18, and then a bunch of 6s. You can put quite a few there. And there we have it. So my displacement is actually going to be approximately 2.8, etc. Now, once we have this, so if that was what was sliding through there, well, then we can find out what work is. So from here, okay, that work is going to be equal to the force that we have. So the force was 492. So times 2.8, etc. Now this will be negative because the force is in the opposite direction as you are moving. So I have here's my displacement multiplied by, and this is 492. And there you have it. So you would have had I'm going to round this to 3 significant figures, 1, 3, and I guess 8, 0 joules, and that's negative. All right, so the object is losing energy, or it's transferring energy out of its system because it's negative, and that makes sense because you have the forces in the opposite direction as you are moving. All right, so that is it. So this one was a great challenge for you. Here's a unit, kind of basically conversion. So it says show that 1 kilowatt hour, which is a very common energy term, when you're talking about electricity and the use of electricity, let's show that it's actually equal to 3.6 million joules of energy, which is quite a lot. So how would we show this? Well, so let's write this down. So 1, kilo, okay, watt hour. Okay, so first of all, 1 kilo, okay, so that just means 1,000, right? So that's 1,000. This is going to be watts hours. So that's the first step that we have. So that's 1,000 right there. Now, notice that it's hours, right? So this is, okay, hours that we would have, okay, in here. So let's, see what this would be. Now, this right here, so 1,000 watts really is 1,000 joules per second, because that's what a watt is. Now, 1 hour, okay, so that means, how many seconds is that? So times, well, there are, 60 seconds in 1 minute. And then there are 60 minutes, okay, in one hour, right? So that's what we have there, okay? And so this hour right here, so that's times the hour, okay, right there. So notice the seconds will cancel, the minutes will cancel, and now the hour and that hour will cancel. And you're going to get exactly, 3.6 million joules. Now, million meaning megajoules, right? So as you multiply this is going to be 3.6 times 10 to the 6 joules, but this of course is mega, right? So, and that would show exactly what they asked for. So it's just a unit conversion. So it's a nice little question to make you think of, how big 1 kilowatt hour actually is. It's quite a lot of energy. That's it for this one. Here's a nice example because it's rather simple. So what is the amount of kinetic energy rehabilitation patient carries when moving at a speed of 1.9 meters per second? Assume the patient has a mass of 67.5 kilograms. Well, okay, so kinetic energy. So within here, so you may recall, so this is 1/2 mass times the speed squared. Well, everything is given in here, so I won't even bother writing the givens because it's actually just a matter of substitution and using the kinetic energy formula. So there you have it, and you can just plug it into your calculator. So 1/2 times 67.5 times 1.9, and that would be squared. So 120, I guess 2, if we round to 3 significant figures. That is it. All right, for this example, pretty simple one. So here's a very nice example. So in this example, they actually are asking us to calculate what the work done is from basically, notice that it's a kind of like a position displacement and a force graph. Okay, so this is really neat because it makes you think about, okay, so what is it? Now, it's actually not that difficult because notice that the directions here are identical. So really, if you're thinking back, work, when the directions are the same, it's just force multiplied by the displacement that you have in there, right? Now, force times displacement, when you're looking at it from the viewpoint of a graph, so now in here, so now notice that on this stretch, so I'm going to just take the first stretch. So on this stretch right here, the force is actually changing, right? So it goes from 0 and it goes all the way up to 30. So however, you can find out exactly what this force times the displacement is for the entire duration. So this is going to be for the first 20 meters that we have in here. So from 0 to 20 meters. So we know that it's 20 meters. We also know that the force goes from 0 to 30, but it goes on a straight line. So really, how you actually calculate this is you just look at the area, that this creates. So notice this is a triangle that you have, and the reason is, because you can take the average force through that entire process. So the average force that you would have is really just, the starting point, which is 0, 30, and if you take half of that, right? So 0 plus 30 divided by 2 is 15. And that's kind of why it's a triangle. So in here, I'm going to actually label this 1 right there. So that 1 is going to be, so the amount of work is 1/2, right? So this is going to be your 30 multiplied by your 20. So 20 is the meters, that's the displacement that you have are carried out. So that's from here to here. The displacement is 20, okay? And then the force is 30 all the way up, but we're taking half of it because we want the average. So within here, so as you can see there, so that's going to be, I guess, 300 joules, and it's positive because they're both aligned in the same direction. All right, so that's all that you would have there. Now, the second portion, so that's going to be the portion which is going from 20, okay, all the way, I guess, to 40, right? So this is this little portion right there. If you're going to do that, notice that here the force is actually constant. So that's going to be your force, and then you need your displacement. Well, 20 to 40 on your position means you went, your displacement is basically 20 meters again. So for this, okay, if I call this number 2, what I'm going to have is this is just 30 times 20, which is going to be 600 joules. All right, so that's what you have right there. Okay, so that's your piece. Now the third piece, so that's going to be this particular piece. So again, this is a triangle. Now it doesn't matter that it's, you know, going downwards, and I'm actually going to capture it from here, okay, all the way up to here because it's very easy for me to do that. So this triangle is going to be, again, so it's 1/2, and this is going to be 30. Now the displacement there, so just be careful because you're going from 40 to 55, it looks like. So that's going to be just 15. All right. So this is 1/2 of 30, I guess that's 15. So 15 times 15 is 225. And, you know, you can double check that if I still remember okay, so 15 times 15, I guess I do. So there you have it. Okay, so that is still positive, by the way. So all of these are positive. Your third piece, so as you're moving along there, so that third piece is going to be, you know, this little piece over here, okay, that you have. Now this is a triangle again, so it's 1/2. Notice it goes to, now be careful because now it's -20 there, right? So the actual force, I'm reading that off from the graph itself, so that's -20. And then, you know, how far of a displacement does it go? Well, it goes from 55 to 65, so that's 10 meters. And so for this one, it's going to be -100 joules. Now it's negative because it's on the negative side, right? So that direction changes. And then now your final piece, okay, so that's going to be another rectangle in here, so that's right here. Okay, so that rectangle right here, what you have is, this is going to be, now that rectangle is -20, that's the force. The displacement goes from 65 to 80, which is 15. All right, so this is what we have over there. Okay, and so, you know, 20, you know, times the 15. Okay, so we have our -300 joules. So those are actually all the pieces that you have. And if you're comfortable in taking triangles and rectangles and understanding that work is just force times displacement, you know, you can certainly compute this. Now, if you wanted the total work, right, so I'm going to, you know, kind of just say the change, right, so that we would have in here in terms of the work, you can certainly add all of these up. So you can add up all the pieces and then see what it will be. So if I go, you know, straight from the first one, so that one was 300 plus the 600, that's the second piece. The third piece was 225, then I had negative, so -100, and then -300, and that would give you that the total amount, okay, of work, at least over that particular distance, would have been positive 725 joules. And that is a pretty nice example with regards to force and then position, okay, graphs that you have in here. All right, so that would be the last example that I have here, okay, within regards to this video. Thanks for watching. See you in our future videos. Bye, everybody.